Good morning. All right, hopefully everybody's doing all right this morning. We are going to finish up 4.2 and probably get into 4.3 today. I did move that homework on 4.1 to 4.3 back to Friday, just in case we need tomorrow to finish that up. But the main thing to focus on right now, just don't forget that you do have test 3 due by midnight tonight. So if you haven't already done that, make sure you get that done. And then once you get that done, right, then you can go ahead and get started on the 4.1 to 4.3 homework. Again, we should get into the shortcuts a little bit today is what I'm hoping. So at that point, you can go back and actually do some of the 4.1 homework and probably do those a lot faster than you'd be able to do them just using the limit laws that we've looked at so far. Okay. I think that's all I've got right now in terms of announcements. So any questions, comments, concerns before we get started? All right, so just to remind you what we were doing yesterday, remember we were looking both at approximations of areas under curves and then finding the exact area under a curve. And so yesterday we did part A here. This is just an approximation, right? So we were using 6 rectangles to figure out an approximation of what that area between the x-axis and the curve would be. Now what we're asked to do in part B is actually evaluate the integral from 0 to 3 of that same function. So we're now finding the exact area under that curve rather than just an approximation. So now we're going to use an infinite number of rectangles to figure out what that exact area should be. Okay, so I'm going to go to the next slide so that we've got plenty of space to work this one out because it will take some space. So we've got our integral from 0 to 3. Our function this time, make sure I have that right, is x cubed minus 6x. And then the dx just tells us that that's our independent variable. All right, now, first things we're going to need here. We need to know delta x and we need to know x sub I because that's what we're actually going to use for our limit definitions. Let me just go back and remind you of that. Okay, so this is what we're actually using now. This integral is equal to the limit as n approaches infinity, the sum from 1 to n of f of x sub I times delta x. Okay, so we're going to calculate our delta x. We're going to calculate the x sub I, and then we're going to plug all that into our summation, and we're going to simplify it to find the exact area. All right, so delta x here, we're doing b minus a over n. So if we think about this problem now, what's our b value going to be for this one? Three, right? So it's always the upper limit of your integral. And then our a value is going to be what? 0. Good. So that's 3 minus 0. That's our upper limit minus our lower limit. And then we're going to put it over n. Well, if there was a set number of rectangles, we would put that value just like we did on the previous problem. It was 6, right? In this case, though, we're doing an infinite number of rectangles. So what's going to actually go in our denominator here? Just n, exactly, right? So since we don't have a set number of rectangles, okay, we're just going to have to put an n in the denominator. That means when we simplify this, our delta x is going to be 3 over n. So that's the width of each one of our rectangles now. Any questions on calculating that? Okay, now the other piece we need is x sub I because that's what we're actually going to substitute into our function. So x sub I, again, I'll remind you of that formula. If you look back here, it's going to be a plus I times delta x. So we just calculated delta x, so we know what that is. We know our a value, so we're just going to plug both of those into this now. So a is 0 plus I times our delta x, which is just 3 over n. So now if we simplify that, 0 plus I times 3 over n is just going to give us 3I over n. Any questions on finding the x sub I using that formula now? All right, now that we know delta x and we know x sub I, now we can actually use our limit definition of an integral to actually evaluate what this is going to be. So we're taking our limit as n approaches infinity. We're taking the summation from I equals 1 to n. And then inside that summation, we need f of x sub I times delta x. So that's our formula now to calculate this integral. Well, we know delta x, we know x sub I, so we can substitute those into this summation now. This just becomes the limit as n approaches infinity, the sum from 1 to n, f of 3I over n times 3 over n. Any questions up to that point, right? Because that's just using the formulas from that previous slide and plugging everything in. Any questions up to that point? Okay. Now, one thing I'm going to tell you is anything that is fixed, right? So when I say that, I'm saying anything that's either a constant or if it has an n in it, because the n value is a number of rectangles, right? It is a fixed number. We can actually bring outside of our summation. So in this case, that 3 over n, I'm going to go ahead and just bring that to the front of the sum so I don't have to deal with it. And all I have to worry about is that f of 3I over n instead. I'm going to rewrite this now as the limit as n approaches infinity. 3 over n comes to the front. Then we still have our sum from 1 to n of f of 3I over n. And that'll always be the case with your delta x. You can always bring that to the front because delta x will never have an I in it. Okay, so only the things with i's are the things that need to stay inside the summation. Anything that's just a constant or an n, we can actually bring to the front of the sum. All right, now we need to evaluate f of 3I over n. Well, we have our function, right, x cubed minus 6x. We're just going to substitute 3I over n into that function now. So now we have the limit as n approaches infinity. And we have our 3 over n out front. We have our summation from 1 to n. And now when I substitute into my function, I'm going to get 3I over n to the third power minus 6 times 3I over n. So just in place of the x values in the function, we're substituting 3I over n there. Any questions on that step? Okay. Now let's simplify what we have inside the summation and see if there's anything else that we might be able to pull out, just like we pulled out the 3 over n. So if we simplify this now, we're going to have our limit, n approaches infinity. We have our 3 over n out front already. We have our sum from 1 to n. If we simplify what we've got in here now, 3I over n cubed is going to give us what? Good, right? So we cube every single piece in there. So 3 cubed is 27. I cubed just becomes I cubed. And when we cube the n, it just becomes n cubed. Okay, so just make sure you're cubing the number and both of those variables when you cube that. All right, now when we multiply 6 times 3i over n, what's that going to give us? Perfect, right? So 6 times 3 is 18. We keep the I over n. And so that's what we've got inside of our sum now. All right. Now, one thing we're allowed to do with summations is if you have addition or subtraction inside of a sum, we can actually split that into multiple sums. So that's the next step. Is I'm going to break this into 2 separate sums separated by that subtraction there. So we're going to have the limit as n approaches infinity. I still have 3 over n. Okay, and now this summation I'm going to split in 2. And so we're going to have the sum from 1 to n of 27 I cubed over n cubed minus the sum from 1 to n of 18i over n. And notice here, I put brackets around both of those sums because remember, this 3 over n now is being multiplied by both of those. So once I split it up, I have to remember that that's going to actually get distributed to both. All right, now that we've split up the summation, right, and again, that's anytime there's addition or subtraction inside, we're allowed to do that. Now we want to look at each of these sums and see if there's anything we can actually pull out front of the summation. So remember, we're allowed to pull out constants. We're allowed to pull out n's because those are fixed values. It's a fixed number of rectangles. The only thing we're not allowed to pull out is i's because that I value is varying along the way in that summation. So in that first sum, 27i cubed over n cubed, what am I allowed to bring out then? So I can take out constants, I can take out n values. We just have to make sure we leave I values inside. So what could I take out of that first sum? Good, right? The 27 over n cubed I can actually bring out. So now we're going to have the limit as n approaches infinity. Again, keep the 3 over n that we've got out here. Now in front of this sum, I'm going to have 27 over n cubed. Now we have our sum from 1 to n. And what's going to be left over inside that sum now? Just the I cubed. Good. And then we have our minus. Now we want to do the same thing with the other sum. What am I allowed to bring out of that sum? Good. The 18 over n. Again, 18 is a constant. N is a fixed number of rectangles, so we can bring those out. Then we're going to have 1 to n. And what's going to be left inside of our sum this time? Just the I. Perfect. All right, let me pause right there. Any questions up to that point about anything that I've done so far? All right. Now, once we get it down to this point and we have the sum of I cubed and the sum of I, this is where those formulas come into play. And like I said, if I give you a problem like this on a test, I would give you the formulas for these. So you just have to be able to get it down to this point so you can substitute those formulas in. So now we're going to have the limit as n approaches infinity, 3 over n. And we have 27 over n cubed times, And in place of this summation of I cubed now, we have a formula that we can use. This is actually going to be n times n plus 1 over 2 all squared. And again, that's just a formula for the sum from 1 to n of I cubed. We can substitute that in there now. Okay, then we're going to have minus 18 over n times, and again, we have a different formula for the sum from 1 to n of I. That formula is just going to be n times n plus 1 all over 2. So once you get everything down in terms of just an I on the inside of your summation, then you'll have a formula that you can actually plug in to get everything in terms of n now. Any questions on that step? All right, so we're almost there. We just got to simplify this and actually find our limit now. Okay, so let's think about how we could simplify this. All right, so what do you want to do first here? All right, so I'm going to make a suggestion here. Let's go ahead and distribute the 3 over n, right? Because that's going to actually get distributed to both of these terms that are separated by the minus. So I'm just going to go ahead and multiply 3 over n times 27 over n cubed. 3 times 27, that's going to give us 81. N times n cubed is n to the 4th. And then this next piece in here now, I can go ahead and distribute the square to everything inside those brackets. So that's going to give us n squared times n plus 1 squared all over 4, because 2 squared gives us 4 in the denominator. Then we have our minus. And now down here, we can actually just distribute and multiply all this stuff together. We have an 18n times n. That's going to be 18n squared. Then we have 18n times 1. That's going to be plus 18n. All over n times 2 is just 2n. It really doesn't matter, what you do first. Follow order of operations, obviously, but you're just going to have to try to simplify this down as much as you can so we can actually evaluate this limit. All right, what's something else we could do at this point? All right, we could distribute the 81 into the 4th, right, and just multiply that out. Notice here, anytime you can simplify, let's do that. Do we have anything here that would cancel out, just to make our lives a little easier? Yeah, we have an n squared in the numerator, an n squared in the denominator that would cancel. So then I'm really just left with 81 times n plus 1 squared over, then we have our 4 and only an n squared left because 2 of those n's canceled out. So always look for those things because that will help you. We could have also done the same thing on the right-hand product over here because we had an n in the numerator and denominator. You could have just canceled those out. We're going to end up doing it at this step anyway. If you wanted to do it up front, you could have done that too. Now, if we divide each of these terms by 2n, what's that going to give us down here? Good, right? So 18n squared divided by 2n is going to be 9n. 18n divided by 2n, the n's cancel out, and that's going to give us, and just make sure here, I'm going to keep this group together, it's going to give us a plus 9. We're subtracting all of that, so that negative is going to have to get distributed at some point. All right, what could we do next? So look at that first fraction. What could we do to simplify that? Good, right? So keep my limit here. Here we can keep the 81. N plus 1 squared is going to give us n squared plus 2n plus 1. That's still over 4n squared. And now I'm going to distribute my negative. Okay, so that's just going to give us a minus 9n and a minus 9. Okay, so I'm running out of space here, so I'm going to create a new slide so we can finish this one out. All right, so we got our limit. N approaches infinity. Add 81 times n squared plus 2n plus 1. That was all over 4n squared. And then we're subtracting 9n, and we're subtracting 9. Make sure that looks right. Okay, good. All right, so what can we do from there? Okay, yeah, go ahead and distribute the 81, right? So that's going to give us 81 n squared. 81 times 2 should be 162 n. And then 81 times 1 is plus 81. All of that is over 4n squared. We have our minus 9n and our minus 9. All right, now let's go ahead and simplify that fraction so we can divide each one of these terms. So what's that going to give us if we do that? Good, so 81 over 4, because the n squares cancel out. Then over here, we're going to have 81 over 2n, right? Because one of those n's cancels. We're still left with one in the denominator. And then we have 81 over 4n squared. And then we still have this. Something's bothering me here. Let me go back and check my work because something's off in this second piece over here. Let me just make sure. That's what it is. Okay. I really do apologize here. Make sure when we do this step, I missed it right here. When we distribute this, remember we also have to distribute it to this term down here, and I missed that step. Okay. So that is going to affect everything that we've got for that second piece, right? So instead of the 9n minus 9, we're going to have something different there. So I'm just going to show you what that should be. I'm going to erase this. I'm going to try to anyway. All right. All right, so instead of that, it should have been minus 18 times 3 would actually give us 54, and the n times n would be n squared. And then we're multiplying that by n squared plus n over 2. Right, which again is going to affect this stuff down here. So instead of 9n minus 9, we're actually going to have the 54 n squared plus 54n over 2n squared. So yeah, so I said make sure you distribute the 3n, and then I forgot to do it myself. So just be real careful there. And make sure any questions up to that point now, once we distribute the 3n and then multiply that out now. And everything in the first part was still okay. That first summation was right. Okay. Now, when we simplify this time, right, the n squares in that first term are going to cancel out. 54 over 2 is going to give us a 27. So we're going to get minus 27 here. And then the second term, 54n over 2n squared, is going to give us 27 over n because one of the n's cancels out. We get minus 27 over n. And then that just stays, minus 27 over n. And the same thing down here, minus 27 over n. All right, so let me write out exactly what we've got now. So this is the limit as n approaches infinity. We've got 81 over 4 plus 81 over 2n plus 81 over 4n squared minus 27 over n. Okay, so that's what it should look like now. And the thing that tipped me off that I had a mistake somewhere, I had that 9n and n is approaching infinity. That means the whole sum is going to approach infinity if I have that there. So you should always get something that gives you a numerical value as your answer. So it should all be constants or n's in a denominator. You should never have an n being multiplied by a coefficient. Okay, so if that happens, go back and check your steps. All right. Now that I've caught my mistake, are there any questions about the steps that got us here? All right, now we can evaluate our limit because now we can just go term by term and think about what each of these limits is. What's the limit as n approaches infinity of 81 over 4? 81 over 4, right? It's a constant. What about the limit as n approaches infinity of 81 over 2n? 0, right? Because we have the n in the denominator. We know that's approaching infinity. That's going to give us a 0. What about the next term, 81 over 4n squared? Also 0. Minus limit as n approaches infinity of 27 is going to be 27 because that's a constant. And then the limit as n approaches infinity 27 over n is going to be a 0. Now it's just a matter of putting all that together. So really it's just 81 over 4 minus 27. What's that going to give us? Good. Negative 27 over 4. Or if you prefer the decimal, that would be negative 6.75. Okay, so either one of those answers, perfectly acceptable. All right, now I do want to go back and look at part A because we approximated what the area should be, right? And in this case, this answer is the exact area, negative 6.75. Our approximation that we got earlier was negative 3.9375. At least it was negative, right? So it told us that more of our area was below the x-axis, but it's not a great approximation. Okay? And so you can see here, depending on what that function is to begin with, it can make a pretty big difference. You know, the more rectangles you use to give you the exact area, this approximation up front was not a great one. Okay? So we got almost negative 4. The actual area, though, should be negative 6.75 instead. Any questions on that part? All right. Now, fortunately for us, the shortcuts are coming, right? Because I don't want to have to do all this work every single time I need to calculate an integral. So we'll have a way, coming up in the next section where we'll actually be able to do this in probably 2 or 3 lines, right? It won't take much at all. Okay, so just know the shortcuts are coming. I do want you to understand this process though, right? How to find delta x, how to find x sub I, how to plug that into your limit definition summation formula, and then how to simplify that down to actually evaluate that limit, right? Because this is what we're actually doing even when we use the shortcut. Okay, the shortcuts just save us a lot of time. All right, we're going to skip example 3. Example 4. So now we want to evaluate the following integrals by interpreting them as areas, right? Because all we're doing when we find an integral is we're finding the exact area under the curve anyway. All right, so the way we're going to do this, we're actually going to think about what these graphs look like, and then we're going to see if we can actually find the area between the x-axis and the curve just by looking at the graph. Well, if we look at this first one, the square root of 1 minus x squared. Okay, I'm going to actually put this into Desmos. Notice here that we're going from 0 to 1, right? So that's all we're focused on in terms of our graph. So let me switch over to Desmos. All right. I'm going to actually reset this window. All right, so we've got square root 1 minus x squared. Again, we're only looking from 0 less than or equal to x less than or equal to 1. I'll zoom in a little bit. Okay, so we're really just looking at this piece right here. Well, if we want to interpret this as an area, what does this look like? It's a quarter of a circle, exactly, right? So if we could think of this in terms of a quarter of a circle and evaluate its area, okay, then we know what the integral should be equal to. Well, how do we find the area of a circle in general? It's pi r squared, right? And if we're looking at a quarter of a circle, then what do we need to do to that? Yeah, divide it by 4 or multiply it by 1/4, right? Either way. So we're only taking 1/4 of pi r squared now. So that's exactly how we're going to do this. Now, what is the radius of this circle going to be? 1, right? Because the center here is at the origin at 0, 0, and the radius here goes off 1 in every direction. So now we're just going to use the area of a circle formula, and we're going to evaluate what this integral should be equal to. So you can see I wrote down the area formula down here, 1/4, since it's a quarter of a circle, and then pi r squared. And we just said that our radius should be 1, so it's going to be 1/4 pi times 1 squared. And if we simplify that, what's that going to give us? Good. 1/4 pi or pi over 4, however you want to write that is fine. Okay, but that is going to be our area. And again, there are no units here because we're just dealing in the coordinate plane. These are just squared units, right? Again, what we just found when we calculated that integral is we're finding this area between the curve and the x-axis just on the interval from 0 to 1 this time, though. Any questions on that part? Okay, so anytime you can actually look at the graph, think of it as a shape, and use geometric formulas to actually evaluate areas, that's going to be a very short way to do some of these problems. Okay. Obviously, it doesn't work on every function because not every one can be, written as a circle or a triangle or a square or something like that. But if it can, that's going to be the shortest way to do it. All right, let's take a look at the next one. Same thing, we want to try to interpret this as area now. So I'm going to sketch this graph first. We're going to see if we have a geometric shape that we can evaluate the area of. What is this graph going to look like? It's linear, right? Okay, and what do we know about this line? Okay, so we're going from 0 to 3, right? And we know it has a slope of 1 and a y-intercept of -1. Perfect. So I'm going to start down here at -1. I'm going up 1 and over 1 because that's my slope. So we go up 1, over 1. That gives us a point here. And I'm going to do that until I get to 3. So we go up 1 and over 1 again. And then we can go up 1 and over 1 more time. So here's my line starting at -1 on the y-axis, going from 0 to 3. It'll look something like this. All right, now we're trying to find the area between the curve, or the line in this case, and the x-axis. So how are we going to do that? Good. We have two triangles this time. If I drop a line down right here, you can see we've got this area up here now, but then we also have this small triangle down here in the negatives with this area over here. Remember, anything above the x-axis has a positive area, anything below has a negative area, so we're going to have to calculate them individually and then subtract that part that's below from the part that's above. Well, how do we find the area of a triangle? Good. 1/2 base times height. Okay, so we're using 1/2 base times height here. So now let's just think about our two triangles. Let's look at the positive one first. What's the base and the height of that bigger triangle up top? Two and two, right? Okay, so it goes over 2, it goes up 2. So we have 1/2, 2 times 2. And then we said we're going to subtract the area of the smaller triangle since it's going to be negative. What's the base and height of that triangle? 1 and 1. So it's only over 1 and down 1 there. So 1 times 1. Now we can simplify. 1/2 times 2 is going to give us what? Good. And then 1/2 times 1 would give us what? It's going to be 1/2. 2 minus 1/2 would be what? 3/2. Good. Or again, if you prefer decimals, 1.5 is fine too. Okay. So there's our answer for that one. Now, I saw somebody put -1 as the height. Just remember, since we're talking about geometric shapes now, in terms of all of these values, we're always just going to use positives. Okay, so the height of that would be 1, the base of that would be 1, and then we're taking into account that it's below the x-axis by subtracting anyway. Okay, so just whenever you're calculating areas, just consider them positive, and then if it happens to be below the x-axis, then make it a negative. Any questions on that one now? All right, so again, just remember, anytime you're calculating an integral, you're looking for the area between the x-axis and the curve. So if you can think of it as a geometric shape, that's probably going to be the easiest way to calculate that area. Okay? All right, now we want to use the midpoint rule here with 5 rectangles, and we're going to approximate what this integral would be equal to. So remember, we've done right-hand endpoints, left-hand endpoints. Now we're doing midpoints. We did that back in section 1 also. All right, so if we want to find this approximate area, what's the first thing we're going to have to do here? So think about, we did example 2, part A, right? We were using right-hand endpoints, but this is going to be very similar. The only difference is we got to find the midpoints instead. All right, go. So we're going from 1 to 2, right? Because we know that's the interval that we're looking at. And we need to break that into 5 rectangles. Right? So I'm going to actually draw this. This is a horizontal segment here. So we can think about it. So we're going from 1 to 2. I'm going to break that into 5 pieces. I'm going to do my best to make these equal. 2, 3, and 4. So 1, 2, 3, 4, 5 equal segments. All right. Now, if we do that, what do we need to do next? Okay. So how did you get 2/5? Why 1/5 instead? So what would be the calculation we would do to actually get that value? How do we find delta x? Okay, so 1/5 is going to be the amount in between each one. I agree with that, right? Because that's the width of each one of our rectangles. But what's our calculation to get that? How do we find delta x? Good, right? So remember, it's b minus a over n. In this case, our b value is 2, our a value is 1, and we have 5 rectangles, so we can divide by 5. When we simplify that now, 2 minus 1 gives us 1, and so we have 1/5 is the width of each one of our rectangles now. So just make sure you remember that delta x formula, because we're going to use it all the time, right? No matter whether it's a set number of rectangles or an infinite number of rectangles, that's how we're always going to find delta x. All right, so now that we know that, that tells me then this first tick mark, right? If this is 1, this is going to be 1 1/5. That'd be the same as 6/5. Then we want to go up another fifth. That's 7/5. Then 8/5. 9/5, and then 10/5 would be 2, right? So those are the tick marks in between 1 and 2, okay, for each one of our rectangles. Now, once we know the width of our rectangle, what else do we need to know? Okay, we've got to find midpoints this time, right? Because that's what we're using. So instead of using 6/5, 7/5, 8/5, and so on, we actually want to know what are the values in between here, because that's what we're actually going to use to calculate our heights. Well, how are we going to find those midpoints? We can average, right? Okay, so I can just add together these 2 points here. So 1 plus 6/5, and then I'm going to divide that by 2. If we do that, common denominator here would be 5. So 5/5 plus 6/5 over 2. That's 11/5 over 2, which would give us what? Good, 11/10. And really, that's 1.1. Okay, that might actually be an easier way to think about it when we actually go to substitute these things in. All right, so we know this value right here is just going to be 1.1. Now we need to find all the other midpoints, right? Now, it's up to you, right? We could continue to average, 6/5 plus 7/5 divided by 2, 7/5 plus 8/5 divided by 2. Or what's the distance between these two midpoints? How far should it be between midpoints now? So not 6/5, right? Because that's the halfway in between, but the distance between them should be 1 over 5 now. So I could just add 1/5 to 1.1 to find that next midpoint. Well, 1/5 is the same thing as 0.2. And so if I just do 1.1 plus 0.2, that's going to give me 1.3 as my next midpoint. So that's this one. Then I can take 1.3 and add 2, or sorry, 0.2. That's going to give us 1.5. That's our next midpoint. And I'm going to do 1.5 plus 0.2. That's 1.7. That's the next midpoint. And 1.7 plus 0.2, 1.9. That's our last midpoint. Okay, so these values right here are the values we actually want to use when we calculate our heights. But again, same thing you would get if you actually average 6/5 with 7/5. That would give you 1.3. If you average 7/5 and 8/5, that would give you 1.5, and so on. Any questions on that part? All right, now that we know the midpoints, what are we going to do next? So why did we even need those midpoints? What are we going to do with them? We got to plug them in, right? Because plugging it into our function is going to give us what? So eventually we're going to get to area, but just plugging these values into our function is going to tell us the what? The heights, right? Okay, so the next thing we've got to find now are the heights of each one of our rectangles. Okay, and again, to do that, we're going to say f of, first midpoint is 1.1. Our function this time is 1 over x. Okay, so we're going to have 1 over 1.1. And honestly, that's going to be a bad decimal to work with, so I would probably just leave it just like that, and then we'll plug that into our calculator as is. Okay, so then I'm going to do the same thing with the rest. We've got 1.3. That's 1 over 1.3. F of 1.5 is 1 over 1.5. F of 1.7 is 1 over 1.7. And F of 1.9 is 1 over 1.9. All right, now our ultimate goal is to find the approximation of the area, right? How are we going to calculate the area now that we know those heights? Okay, good. Times what by 1/5 though? Because 1/5 is the width. I'll call it 0.2. All the heights added together, right? So make sure you're summing them up. So it's going to be 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. Okay, so those are the heights of all of our rectangles. And then we're going to multiply that by the width, which we said is 1/5 or 0.2. Now we can just put all that into our calculator, get a decimal. So what would the approximate area be this time? Two decimal places is sufficient here. Perfect. 0.9 would be our approximate area using midpoints here. Okay. Again, same process as before, right? We're finding our delta x, which is the width of our rectangle. We're thinking about where those midpoints are going to be this time, right? Not just the right hand or left hand endpoints. We have to average those values to find those midpoints. Once we know those values, plug them into your function to find your heights. And then it's always the width times the sum of the heights. That's how we're always going to calculate the area. Any questions on that one now? Again, keep in mind, this is an approximation, right? This is not the exact area, because to get the exact area, we would have to do the limit as n approaches infinity of that summation, right? So just keep in mind, this is not exact, this is an approximation. All right, now, some rules for our definite integrals. if we have the integral from a to b of f of x dx, if we switch our limits of integration and we put a as the upper limit, b as the lower limit, we just have to put a negative on the outside. Okay, so anytime you switch your limits of integration, just make the integral a negative, and those two things are going to be equal now. Okay, now our next rule here says that if we have an integral from a to a of f of x dx, that's going to be equal to 0. Well, notice here, our upper and lower limits are the same value, meaning that we have no width whatsoever to our interval, which means there's no area. Okay, so if your upper and lower limits match, okay, then it's always going to be equal to 0 because there's no area there. Now the next one here, this says the integral from a to b of c dx, where c is a constant, is going to be equal to c times b minus a. Now let's think about why that is. I'm going to actually graph this one. What would the graph of c look like? So you just had c as a constant. What would that graph look like? Let's say, for instance, that constant was 5. What would that graph look like of 5? It's a horizontal line, right? Okay, so anytime you've got a constant function, you're just going to have a horizontal line. So I'm going to put my constant here. I'm going to say I've got this horizontal line at c. Now, in this case, we're only going from a to b. Those are our x values. So I'll put a here. We'll call this b down here. So I'm only looking at the horizontal line segment from A to B. If I want to evaluate the area between the x-axis and that horizontal line, how could I do that? Think about the ones we did with geometric shapes. Is there any way I could calculate this area using a geometric shape now? Exactly, right? So it's either a square or a rectangle, right? We're not 100% sure. It's at least some type of rectangle, right? But if we calculate this area now, the length at the bottom would just be the difference between A and B. So that's the B minus A piece. And then the height of that rectangle would be C, and that's where the C comes from. So this is really just saying we're multiplying base times height. That's where we get C times B minus A. So again, if you just want to think of that one geometrically, right, you could get it that way. But you could also just use this formula here where it's the constant times B minus A. That'll also give you the same area, okay? All right, now the next one here just says if we have addition, and then subtraction comes later, but if we have addition or subtraction in an integral, we're allowed to split that up, just like we did with our summations, okay? So if you have a sum with a plus or minus in it, we can split it up. Same thing with an integral now, we can split that up. Notice here, keep the upper and lower limits of your integrals the same when you do that, though. Okay, that's key. All right, and then the next one here says that if we have a coefficient being multiplied by a function, we're allowed to move that to the front of our integral here, so we can just bring out that c value. And then the last one here, if we have two integrals where the upper limit of one is the same as the lower limit of the other, and we have the same function on the inside, we can combine those now and just take the integral from a all the way to b of that function. Well, if you think about it, right, we're basically saying, well, we're going from a to some value of our function, that's an area. Then we're finding c to some other value, b, that's an area. We're adding those areas together, which is really just going to be the area all the way from a to b anyway. Okay, so that's what we're doing in this case. Again, function inside has to be the same. Upper limit of one has to be the same as the lower limit of the other. Then we can combine them. Any questions on those properties of integrals? All right, let's take our break here, and then we'll come back and do example 6 where we apply some of those properties. Okay, so I've got 11 o'clock, so 11:05 we'll get started back up. All right. So example 6, we want to use those properties we just saw to evaluate this integral from 0 to 1 of 4 plus 3x squared dx. All right, so thinking about the properties we just looked at, what's one thing we could do with this integral first? Okay, good. So since we have addition in there, we're allowed to split it into two separate integrals. I'm going to write this as the integral from 0 to 1 of 4 dx plus the integral from 0 to 1 of 3x squared dx. So anytime you have addition or subtraction, you're allowed to split that into two separate integrals. Again, just keep the upper and lower limits the same. All right. What else could we do now? All right, good. So the one on the left here is a constant. And remember, we had a formula that said we can just take the constant times b minus a. So that's just going to become 4 times 1 now for that one. All right. Is there anything we can do with the one on the right here? Good. Anytime you've got a coefficient, we're allowed to bring that outside. So we're going to bring the 3 out. So it's going to be the 3 times the integral from 0 to 1 of x squared dx. Now, eventually we'll have the shortcut to do the integral from 0 to 1 of x squared dx. If you remember, though, we've done this one. Does anybody remember what that value was when we calculated the integral from 0 to 1 of x squared? It was the second example we did in section 4.1. It was 1/3, right? And so now this is just going to be 4 plus 3 times 1/3. And then if we simplify that, what are we going to get? That's going to be 5. Perfect. Okay, so this right here would be our answer. And again, eventually we'll have a shortcut that tells us what the integral from 0 to 1 of x squared is, right? So we'll be able to do that. For right now, I'm just pulling that 1/3 from the example we've already done. Any questions on applying those properties here? All right, example 7. So if we know that the integral from 0 to 10 of f of x dx is 77, and the integral from 0 to 8 f of x dx is 12, we want to find the integral from 8 to 10 of that same function. All right, so again, using those, all right, it is going to be that, right? So let's think about using the properties that we just saw, how we could actually set this up. Well, we know if we have the same value as our upper limit on one and the lower limit on another, we can add those together to get the total area from A to B, right? So I can actually say, well, this is going to be the integral from 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx should be equal to the integral all the way from 0 to 10 now, right? Because the upper limit of the first one is 8, lower limit of the second one is 8. So now I can go all the way from 0 to 10 of f of x dx. Now we're just going to substitute what we know. The integral from 0 to 8 of f of x dx is 12. So I can put 12 here. we're looking for the integral from 8 to 10 of f of x dx. So this is what we're trying to solve for. And we know the integral from 0 to 10 of f of x dx is 77. And so if I want to get the integral from 8 to 10 by itself now, what would I have to do? Just subtract the 12. So now we have the integral from 8 to 10 f of x dx. 77 minus 12, that should give us 65. And so this would be our value here. Now, you don't have to write out all those steps every time, right? Because if you just recognize it as, oh, the total area is 77, I can subtract the area from 0 to 8, and that'll give me what's left over from 8 to 10. That's perfectly fine. The only reason I say, it's especially on the test, you might want to write out the steps. I could combine some of the properties where maybe you're switching the limits of integration and making one negative, and you're trying to combine them into one. At that point, the signs get a little tricky, right? And so just be real careful that you don't make a mistake there in your signs. Any questions on that one now? All right. So that's all we're going to do in that section now. So we're going to move on to 4.3. All right, so 4.3, the fundamental theorem of calculus. And there's two parts to this fundamental theorem, and we'll look at both of them. Hopefully we'll get to both of them today. But what this is going to allow us to do is see the relationship between all the things we've done previously and what we're doing with integrals now, and this is where the shortcuts are going to come in. All right, so example 1. If f is a function whose graph is shown, and g of x is the integral from 0 to x of f of t dt, so our graph here is f of t, we want to find g of 0, g of 1, g of 2, and so on, okay? Those are the values we're trying to find. So let's think about what this is asking us then. If we're looking for g of 0, well, 0 is an x value. So we're looking for the integral from 0 to 0 of f of t dt. What would the integral from 0 to 0 be? It's 0, right? If the upper and lower limits are the same, we had a property that said that should be 0, because in this case, there would be no area in that region, because there is no region. Any questions about how we got that one? All right, now let's look at g of 1. Again, that's our x value, so that becomes the upper limit. So we're looking for the integral from 0 to 1 of f of t dt. How could we find the integral from 0 to 1 of f of t dt using that graph now? It's a triangle, right? So we're just finding the area from 0 to 1. So we're looking for the area of this triangle right here. So how would we find the area of that triangle? Good. 1/2 base times height. Our base this time is 1. Our height is 2. And so what's that area going to be? 1. Perfect. And again, it is positive because it's above the x-axis, so we get a positive 1 here. Any questions on g of 1? All right, g of 2. So now we're looking at the integral from 0 to 2 of that function. How are we going to do that? Okay, good. We have the triangle that we already had from 0 to 1, and now we have a rectangle, right? So now I'm just adding in this additional area here. How are we going to find that piece just from 1 to 2? Length times width, which is 1 times 2. Good. So I'm taking the area of the triangle we already found. That's 1. I'm adding the area of our rectangle, which is 1 times 2. So what's that total area going to be now? 3. Perfect. So our integral from 0 to 2 now is the area of that rectangle plus the area of that triangle, which is a total of 3. All right, now we want to find g of 3. So we're looking for the integral from 0 to 3 of our function. Now, this one we're going to have to approximate a little bit because it's not a nice shape like the triangle and the rectangle were. If we're going all the way to here now, we want to know total area in here. Well, we know for sure we've got the triangle and the rectangle, which is 3, plus whatever we think this area in here is going to be. So if you had to take a guess, an approximation, what would you approximate that area to be there? Okay, so it's bigger than 1 because it's more than just the triangle would be, right? And I would say it's definitely less than 2 because that would be the whole rectangle. So it's somewhere between 1 and 2, probably closer to 1. So 1.3 is not a bad guess, right? So 1.3 is fine. If you had said 1.4 or 1.2, something like that, I'd be fine with that answer also. But again, bigger than 1, less than 2, probably closer to 1. Okay. All right, so that's going to give us 4.3 as that total area now from 0 to 3. Any questions on that one? All right, g of 4. So now we're going all the way from 0 to 4, f of t dt. Well, we know our total area from 0 to 3 is 4.3, so we can start there. Now we're going to here, though. So we need to include all of this area. Well, what do you think the area there is going to be? Good. Because it's below the x-axis, it has to be a negative, and it looks like it's symmetric to what we just looked at, so we could call it 1.3 again. So this time we're actually going to subtract 1.3, and when we do that, we're actually going to get 3 again. So because that area above and that area below basically just cancel each other out, we're back to that same area that we had from 0 to 2 now. Any questions on that one? All right, our last one, g of 5. Now we're looking for the integral from 0 to 5. So again, we can start with the 3 that we just had from 0 to 4. Now we're adding in this additional area over here. So what is that area going to be? Negative 1.3 again, right? Because it looks like it's the same as the one before it. And so if we subtract that, what should we get? 1.7. Good. Okay. Any questions on those? So again, just keep in mind, anytime you're finding an integral, you're looking for the area between the x-axis and the curve. Anything above is positive, anything below is negative. Just keep that in mind. The total area in this case for that curve from 0 to 5 would be approximately 1.7, right? Because we have so much negative area down there that it cancels out a lot of that positive area, but there is still a little bit more positive than negative. Any other questions there? All right. So here's part one of the fundamental theorem of calculus. If f is a continuous function on a closed interval from a to b, the function g, defined as g of x equals the integral from a to x, where a is just a real number, okay? It doesn't matter what real number it is, just some real number up to a variable x of f of t dt. It's going to be continuous on that same interval and differentiable on that interval, open interval from a to b. And in this case, g prime of x is going to be equal to f of x. In other words, if I take the derivative of this integral that's given up here, all I really have to do is substitute that x value into our function, and that's going to give me the value of our derivative. Okay? So the derivative of an integral from some value to x of f of t dt is just going to be equal to f of x. Now, let's actually apply that to an example. So we want to find the derivative of this function. Okay, so our function here is defined as the integral from 0 to x of the square root of 1 plus t squared dt. If I want to find g prime of x, what are we going to do? Okay, we don't have to go that far. So don't make this harder than it is. Look at part one of the fundamental theorem of calculus. If we have an integral from some value to x and a function in terms of t, and we're taking the derivative of that g function, what are we going to do? Exactly, right? We're taking the x value, we're substituting it into our f of t function. So in this case, everywhere I see a t, it becomes an x, so we get 1 plus x squared, and we're done. That's part one of the fundamental theorem of calculus. So again, any integral, and it doesn't matter what the lower limit is, right? In this case, it's 0. It could be any real number. From some number to x of a function in terms of t, if we take the derivative of that function now, we're just going to substitute that upper limit x into our function, and we're done. Any questions there? All right. Now, the Fresnel function, okay, s of x is equal to the integral from 0 to x of sine of pi t squared over 2 dt, named after a French physicist, blah, blah, blah. All we care about here, though, is we're looking for s prime of x, okay? So if I want to find the derivative of that function now, what can I do? Yeah, just change the t to an x, right? Okay, it's the same type of thing. We've got a function, it's an integral from some value to x. We've got a function in terms of t. I'm looking for the derivative. All I have to do is plug in x in place of t. So we're going to get pi x squared all over 2, and we're done. Any questions on that one? Okay. There is a question like this on the test. please don't miss it, right? There's little work, right? Um, I'm not going to worry about the graphs here. Okay, so as long as you know how to actually evaluate that using part one of the fundamental theorem, that's all I really care about on this one. Okay. If you wanted to look at the graphs, you could just to see how they're related to each other, but I'm not going to do that here. Okay, but again, on the test, there will be one where you're using part one of the fundamental theorem. Please make sure you know how to do this, right? Because it should be easy points. Okay, but I always have people that don't, and then they try to evaluate that integral and then substitute an x in, and they show all this work and it's wrong, right? Okay, because all you really have to do here is just plug that x value in. Okay. All right. Now, this time we're taking the derivative of an integral from 1 to x to the fourth of secant t dt. Now, we have to be careful here because our first part of the fundamental theorem just says if the upper limit is x, then we can just substitute it in when we take the derivative and we're done, right? This time we've got x to the fourth up there, though. Okay, so we've got something other than an x. So what we're going to actually have to do this time is do a u substitution so that I can actually put a u up there instead. That'll be the thing I substitute in, but then we're going to have to consider what else changes about this. Okay, so for right now, I'm going to let u be equal to x to the fourth. And I'm going to rewrite my integral as the integral from 1 to u of secant t dt. So that part's not going to change. Now, if I want to use part one of the fundamental theorem to be able to just substitute that u into my function, what would I need out front of this integral now? What would I need to do to that integral to be able to just substitute that u value in there? We need the derivative, right? Okay, now, if I'm taking the derivative of this integral, I need to be taking the derivative with respect to what variable? Okay, so if I want to be able to substitute u into my function, I actually need to be taking the derivative with respect to u instead. So out front here, I'm going to put d du. Okay, so instead of d dx, I want d du, so that then I can just use my part one of fundamental theorem, plug the u value into my function. Now, the issue there is that I've changed what I had in front of my integral, right? So the u is fine because it's equal to x to the fourth. It is. It's that's all this is applying chain rule now when your limit of integration is something other than x. Okay? So we have to think about what else we're going to need out here now to kind of balance this out so that it actually matches up to what we started with. Well, if I put a d du out front and I started here with d dx, what else would I need to multiply by out here so that it's actually the same thing that I started with? All right, so not x to the fourth, right? Because that's just our u value. We've already got that in the integral. So I'm trying to say if we've got d du out front now, but I had d dx to start. Okay, so I agree with that. What's another way to write that, though? How else could you say u prime? Because I just want to show how everything cancels out and it actually lines up with what we started with. What's another way to say u prime? Okay, tell me this. U prime is the derivative of u with respect to what variable? not d. The thing about what u is equal to over here, if we find u prime, we'd be taking the derivative with respect to what? It's x, right? So this is really just du dx. So I'm going to put du dx out front here. Because if we do that, the du over du cancels out, and I would actually have d dx, which is what we started with up front. Okay, so that's why we need that du dx here, so that now this matches exactly what we started with. The u is x to the fourth, and this product out front is equivalent to d dx. So now I just need to know what is du dx. Well, I can calculate that over here. So what is du dx going to be? Four x cubed, right? So just using our power rule, that should give us 4x cubed. Now we can just substitute everything in. So we're basically saying this is 4x cubed times, and what is the derivative with respect to u of the integral from 1 to u of secant t dt going to give us? So we're taking the derivative here with respect to u of an integral that goes from some value to u. So what can we do now? So what if this was d dx integral from 1 to x of secant t dt? What would you do? You'd substitute the x in and you'd be done, right? Well, in this case, instead of an x, we've got d du of that integral from 1 to u. So what are we going to do instead? Substitute a u, right? So this just becomes secant u. So because we're taking the derivative of an integral whose upper limit is a variable, okay, as long as you're taking the derivative with respect to the same variable that's up there, first part of fundamental theorem says we can just substitute that variable into our function on the inside now. Now, the last step, we just need to substitute that u value back in to get everything in terms of x. So we have 4x cubed times the secant of x to the fourth, and there's our answer. Any questions on how we got that? Okay. Now, I think it was Hyro that said this earlier. It reminds him of chain rule. That's all it is, right? So we're still just substituting x to the fourth into our trig function in this case, which is secant x to the fourth. And then we just have to remember, because there's more than just an x there, we have to have the derivative of that inside piece. That's where the 4x cubed comes from. Okay, so if you just recognize that, okay, you don't have to write out the steps like this every time. Okay, just don't forget, if there's something other than x there, we need the derivative of whatever that is. Okay. All right, part two. Okay, so this is the big one. If f is continuous on a closed interval from a to b, the integral from a to b of f of x dx is big F of b minus big F of a, where f is the antiderivative of f. So if you remember back in the last section of chapter 3, 3.9, we started doing antiderivatives. That's where these are going to come in now. Okay, so this integral, if we can calculate the antiderivative of our function on the inside, then we can just substitute our upper and lower limits in there, subtract those values, and that will actually give us what that integral is equal to, which is, again, the exact area under the curve or between the curve and the x-axis along that interval now. So this is our shortcut. Find your antiderivative, plug in your values, subtract, and that's going to give us our answer, rather than having to use that long limit definition that we did before. Okay? All right, so let's try this one now. So we want to evaluate the integral from -2 to 1 of x cubed dx. So again, first step here is we've got to find the antiderivative. How would you find the antiderivative of that inside function? Or just what would it be? Good, right? So in this case, we raise the exponent by 1. That gives us x to the 4th. 1 over the new exponent. That's 1/4 out front. And now I'm going to put a vertical line over here to the right, because now we're evaluating this from -2 to 1. Okay, so we have to remember those limits of integration. So we use a vertical line to the right to indicate the values that we're going to substitute in. All right, so now that I have my antiderivative, now I can plug the values in. Make sure that you're plugging them in the correct order. It's always the upper limit first minus the lower limit. So we're going to have 1/4 times 1 to the 4th minus 1/4 times -2 to the 4th. So I'm plugging the 1 into my antiderivative, plugging the -2 into my antiderivative, and then subtracting whatever values we get there. Okay, if we do that, what's 1/4 times 1 to the 4th? Good, that's just 1/4 minus, and then 1/4 times -2 to the 4th should give us what? Good, that's 16 over 4, which is 4. And if we subtract that, what do we get? Good, -3.75. Or again, if you prefer the fraction, that would be -15 over 4. Either one of those answers is fine. Again, that is the exact value of the area under the curve x cubed on the interval from -2 to +1. And again, keep in mind, because we get a negative area, that just means that more of our area this time is below the x-axis. And if you think about the curve x cubed, it's going to look something like this. And so if we go from -2, say that's over here, it's going to be all this area here, and then we're only going to +1. It's going to be this area in here. Right? So more of the area is below than is above, and that's why we get a negative area overall. So the reason we use the antiderivative is because part 2 of our fundamental theorem tells us that's our shortcut. If I want to know the integral from a to b of f of x dx, I'm going to find the antiderivative at b, I'm going to find the antiderivative at a, and I'm going to subtract those two values. Okay? So big F, remember, represents an antiderivative of little f. And so we take the antiderivative of our inside function, we plug in the a and b values, and we subtract. Always plug in first and a second. Okay? So yeah, so this is the shortcut now, right? So rather than having to use the limit as n approaches infinity of that big summation, now if we can find the antiderivative, right? We can't do that for all functions right now. Okay, but any function that we can find the antiderivative of, that's going to be our best bet, because just plug in those values and we're good to go. Oh, okay. So, Dean, in this case, with a definite integral, which is what we've been working on so far, you're going to get a numerical value, and so there is no plus c. When we start doing indefinite integrals where we don't have limits of integration, then we're going to have the plus C again, just like we did with our general antiderivatives. Okay, so it just depends on whether you have numbers for your upper and lower limits or not. That's how you determine if you're going to have the plus C or not. Okay. Yeah, when we start doing indefinite with no number there, then we're actually finding a function, and then it will have the plus C. Any other questions here? All right. So let's look at this one. We want to find the area under the parabola y equals x squared on the interval from 0 to 1. All right, so first thing we've got to do here is think about how we're going to set this up. So if we're looking for an area under the curve, y equals x squared from 0 to 1, what's the setup going to look like for this one? All right, good. We've got our a and b values, right? That's 0 and 1. What else? All right, our function is x squared, right? So here's our f of x. And if we're looking for the area, what are we going to use? Okay, we are eventually going to do that, right? But let's just get the setup first, right? So anytime you're looking for an area under a curve, we're going to use a what? So we don't need delta x, right? Because in this case, we have shortcuts now, so we don't have to do all that extra work with our limit definition and everything. Okay, so what's going to give us the area under the curve? What do we need to calculate here? An integral, right? So we're going to take the integral here from a to b, which is 0 to 1, of our function x squared, and then we need the dx just to indicate that our independent variable is x. So that's the setup for this one, right? Anytime they give you the interval and they give you the function, we're looking for the area. It's the integral along that interval of our function. Any questions about that? All right. Now that we have our integral set up, what can we do next? Now we can take the antiderivative, right? Because that's our shortcut to evaluate this integral. What's our antiderivative going to be this time? Perfect. 1/3 x cubed. Again, we're evaluating that from 0 to 1. All right. What do we have to do now? Good. Now we plug in our values. Remember, b goes in first, a goes in second. So it's going to be 1/3 times 1 cubed minus 1/3 times 0 cubed. So if we simplify this now, what are we going to get? Just 1/3, right? The second term becomes a 0. 1/3 times 1 cubed is 1/3. There is our area under the parabola x squared from 0 to 1. That's the second example we did in this unit, right? So if you think back to section 4.1, example 2, where we had to use the limit definition to calculate this, and it took up basically a whole page, now we can do it in like 2 or 3 lines, okay? So find your antiderivative, plug in your upper and lower limits, subtract those values. That's going to give you the exact area under the curve now. There's one question where you would have to use, well, maybe. I haven't decided yet whether I'm going to put one of the long limit ones on there or if it's just going to be one where I ask you to approximate with a specific number of rectangles. So make sure you know how to do both. but there will at least be one where you're either approximating using delta x and finding the values to plug in for your heights, or you're using that limit definition, okay? And then everything else you'll be able to use the shortcuts. Any other questions here? Yeah, I have to take the test myself and see how long it takes, and I always want to make sure I give you enough time in the 2 hours to get it done. And I know the limit ones take a while, so it could be one of those if I don't have a ton of other questions. But a lot of times I like to put more questions so they don't count as much each. So that would mean in that case I would use one of the approximate ones instead with a set number of rectangles. All right, so let's try this one. This will be the last one we do. We want to find the area under a cosine curve from 0 to b, where in this case, b is somewhere between 0 and pi over 2, right? And we've done something similar to this. Remember, we have our cosine curve. Starts at 1. Pi over 2 is going to be that first x-intercept. So it's going to curve down like this, hit that value. We're saying there's a b value somewhere in between. Right? We don't know exactly where, and we want to know just the general area, no matter where that b value happens to be. All right, so how are we going to set this one up? All right, good. So we're taking the integral. In this case, we want to go from 0 to b because that's our a value and our b value. 0 to b. And then we have our cosine x function. And then don't forget we need the dx just to say that's our independent variable. All right, so what can we do at that point? Now we need the antiderivative. Good. What's the antiderivative of cosine? Okay, so be careful. Antiderivative of cosine is actually going to be just sine, right? Okay, because the derivative of sine would give us cosine. Okay, so we're going to get sine of x. And we're evaluating that from 0 to b. All right, so now we can do what? Good, now we can plug in our values. Remember, upper limit goes in first, so we're going to have sine b minus sine 0. Well, what's the sine of 0? Just 0, right? So that's going to become a 0, so this is now just sine of b. That's our answer, okay, because we're just saying there's some general b value between 0 and pi over 2. So now I know no matter what that b value is, if I want to know the area between 0 and that value, I can just take the sine of that value, and that gives me my area. Any questions on that one? All right, so like I said, that's where we'll stop for today. Just a couple of reminders. Don't forget the test 3 is due by midnight tonight. Okay, so if you haven't taken that already, make sure you get that done before midnight. The homework for 4.1 and 4.3 is going to be due Friday at midnight. We'll definitely finish up 4.3 tomorrow, so you'll have everything you need to finish that one. And then next week, we only got a couple of days, so we'll kind of play it by ear, see how far we get. and I'll adjust that next homework as necessary. But again, the next test will not be until after the 4th of July holiday. Okay, so just keep all that in mind. Let me know if you've got any questions about anything. Have a great afternoon, and I will see you all tomorrow.